Hello, this is the application of volume. In particular, it's finding volume using disks and sometimes washers. A disk you could think of like a frisbee, a washer you could think of like the accessory that you might use when you're building furniture. It's kind of shaped like a flat donut. So it's a disk with a hole in the middle. To find volume, you are integrating a bunch of areas. And since we are using disks, you could think of that as an area of a circle. And if it's a washer, it's the area of a circle minus the area of the smaller circle inside. And you'll see examples of both of these in just a few minutes. The trick here is to really be strong at visualization. So I find it helpful in order to sketch the scenarios. So let's just jump right into it. In our first problem, we want to find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals root x from 0 to 1. So over here, I've got the function y equals root x sketched out. If you rotate about the x-axis, then you're going to end up getting an object that kind of looks like a bullet. And since we're rotating about the x-axis, I am going to envision taking this cross-section. That's my disk. And that disk has R in this region. Now this disk, I'm slowly going to go along this x-axis. And so my disk, you could see from left to right, are going to increase. But in general, each disk is going to have an area of pi r squared, because that's the area of a circle. Now r is in the y direction. It's going up, down. So that means this is pi y squared. So this is the thought process. I first start with the area of the shape. I figure out, does r, the radius, correspond to y, or does it correspond to x? And I plug that in. And then what I do next is I remember that we were told that y equals root x. So it's at this point that I substitute in the functional form for y in terms of x. So this is pi root x squared, and the square of the square root is just x. So we've got pi x. So now I have finally figured out my a function. To get the volume, I want to integrate this. So this is pi x dx, and that is going to be integrating from 0 to 1 along the x-axis. Remember, pi is constant, so integrating x, we've got pi x squared over 2, integrating from 0 to 1, and that is going to come out to just pi over 2. So the next problem asks us to essentially derive a volume that we learned back in high school or junior high, somewhere around there, and that is that the volume of a sphere is 4/3 pi r squared. You know, up to this point, you'd probably just been told that, but you may not have been shown why. And now you have the background to do so. So you think of, okay, sphere, if I think of two-dimensional, it is going to be a circle. And a circle, a general circle of radius r, is x squared plus y squared equals r squared. Solving for y, that is going to be plus or minus the square root of r squared minus x squared. I only sketched the positive portion. So the curve that you see is y equals positive square root of r squared minus x squared. You only need half of this circle. And it really doesn't matter which half you do. I just use the top portion because then I could integrate with respect to the x-axis. If you use the right side, you know, as a function of y, you'd be integrating with respect to the y-axis. So what I'm going to do in order to create a sphere, I am going to rotate about the x-axis, which means that our circle looks like this. And remember, it's being rotated about the x-axis, so this is going to be a sphere. I'm going to take a cross-sectional disk right there. This is my radius r. And now I'm going to start figuring out what the area function is. So a, again, is pi r squared. And the radius is in the y direction. And we know that y is going to be the square root of r squared minus x squared. So when we square that, we have pi r squared minus x squared. This, let's see. So we want to now integrate this. So we've got the volume is the integral of pi r squared minus pi x squared. And we're integrating from negative r on the x-axis up to positive r. It's important to keep that detail in mind. Let's go ahead and integrate. So we've got pi r squared x minus pi x cubed over 3. We're evaluating this from negative r to positive r. And this is, let's see, pi r cubed minus, you've got 1/3 of pi r cubed minus, when x is negative r, we have negative pi r cubed minus pi over 3 times negative r cubed, which is going to make this positive. And so we've got 1/3 pi r cubed. And now we can start simplifying. So I see that this minus sign out front is going to make this one positive, and this one will be negative. So I've got 2 pi r cubes and I have 2 negative 1/3 pi r cubes, which is negative 2/3. And with a common denominator of 3, this comes out to 4/3 pi r cubed. And I'm just realizing I have a typo over here. That should be 4/3 pi r cubed. So that is the volume, and that's where it came from. Problem 3. So problem 3, I set up to have 2 parts. It's the same idea, but we're going to determine the volume of the shape depending on whether we rotate about x and rotate about y. So first we're going to tackle the x scenario. Over here, we have 2 curves, y equals x and y equals x squared. I've sketched them over here. And in the first scenario, we are going to rotate about the x-axis. So here is our y equals x, and our y equals x squared. Rotate about is going to give us that. And I'm going to take this cross section here, which you'll notice if you visualize this shape, it's kind of like a flower. You got these petals on the outside, you have petals on the inside. You really only want the volume of what's happening in between. So this is a washer. We're going to have two radii. The outer radius goes to the y equals x function, and the inner radius goes to the y equals x squared function. So our area is going to be pi r outer squared minus r inner squared. The radii are in the y direction, so this is pi y outer squared minus y inner squared. And now substituting in the appropriate functions in the right places. The outer radius goes up to y equals x, so this is x squared. And the inner radius is y equals x squared. So this is going to be x squared squared, which is x to the fourth. And that is the area function that we want to integrate. So the volume is the integral from 0 to 1. And I found that by setting the two functions equal. So I'll do that on the side just in case you don't see it. So if the two functions intersect, then x equals y can be subbed into the y on the y equals x squared. So you've got x squared equals x, which is x squared minus x equals 0, which is x times x minus 1 equals 0, which means that x will be 0 or 1. That's the only way that product is going to be 0. Now, substituting the area function in, we've got pi x squared minus x to the fourth. And integrating this, we get pi x cubed over 3 minus x to the fifth over 5. Evaluate from 0 to 1, which is going to give us pi times 1/3 minus 1/5. And getting a common denominator, let's say of 15, we're going to have 5 minus 3, or 2 pi over 15. So that is the volume of the object that I sketched to the left. Now, what if we rotate about the y-axis? What's going to happen is that now our shape looks like this. And our washer might be that cross section. There's still two radii to consider. You've got the outer radius corresponding to the y equals x squared function, and you have the inner radius corresponding to the y equals x function. So we need to work out our area function here. And so A is pi r outer squared, but this is in the x direction, so this is x outer squared minus x inner squared. The outer function, solving for x, so the outer function is y equals x squared, which means x equals root y squared, minus the inner function, which is y equals x, so x equals y squared. And just to simplify a little bit, we've got pi y minus y squared. Now we set up our volume equation. So volume is the integral of that. And we need to figure out what our y values are. So we know we're going from 0, and at 1, y equals x, y is going to be 1. So our limits of integration actually happen to have the same values. Now we integrate. So we have pi times y squared over 2 minus y cubed over 3. Integrate or evaluating from 0 to 1. And this is going to be pi times 1/2 minus 1/3, which with a common denominator of 6 is going to give you pi over 6. So this is a great example of two things. One, to see how to do the volume, whether you have washers in the x direction or the y direction, but also to just demonstrate that maybe intuitively you might have expected the same volume, but the volumes actually differ. And so depending on how you rotate, it does impact the volume more often than not. And that is it for the examples of how to use discs and washers to find volumes.